Good morning. Welcome to Casual Friday at the Malkan apartment. I think it would be a good time to have a cup of tea. There's just so many possibilities for product placement here, which I will avoid. But anyway, there's one of my favorite tea bags here. Oh, I need some boiled water. All right, 1 cup boiled water. Well, I have it right here. And I'm going to put it into a hot pan that has been sitting here on the burner. All right, it's pretty hot. All right, but not yet boiled. So that went from room temperature. Now I'm putting it on the burner. We'll see how long it takes for that to boil. Actually, it's making pretty good progress right away. We'll bring that to a rolling boil and then see what the next step is. I guess we're talking about heat and its effects on raising temperature of things, particularly when it raises the temperature enough to change the phase of the material. Let's first look at this interesting table here of what's called specific heats of everyday stuff that you have in a kitchen, I guess. Silver, well, we don't have any of that. Copper, glass, water, yeah, we got that. Alcohol, there's a little bit of that in here. And so this column here tells you what you want to know. The amount of energy it's going to take to raise a kilogram of this material. If you have a pure block of aluminum, 1 kilogram, how many joules, or actually how many thousand joules, how many kilojoules is it going to take to raise that by 1 degree Kelvin or 1 degree centigrade, right? It's the same thing. Well, you notice that for these various metals, it varies quite a lot from something like mercury, which doesn't require very much energy at all to raise it 1 degree, up to aluminum, which requires a lot. But what are the huge ones here? Look at this. The liquids have enormous specific heats, especially, yeah, I'm talking about water at the bottom of the table. As you may recall, it takes 4,180 joules of energy to raise a kilogram of water by just 1 degree Kelvin, right? Or if you want the definition of a calorie, remember a kilocalorie was 4,180 joules. By definition, 1 calorie is enough to raise 1 gram or 1 cubic centimeter of water by 1 degree. So a kilocalorie, 1,000 calories, is enough energy to raise 1 kilogram of water by 1 Kelvin. So it's obvious just looking at this table that compared to other solid elements here, water has an enormous heat capacity. We'll look at what the heat capacity for gases is in a minute. That's simpler to do. Oh, look, it's already boiling after just about 2 minutes. All right. Now I'm going to do an experiment. Suppose, and this really does happen, suppose I was just so wrapped up in work or something or a physics lecture that I completely forgot to turn off the heat to the burner to make my tea. It's going to keep, well, what's it doing now? It's boiling. All right, you can't see it. It's boiling there. That's going to take quite a while. So I should be safe, actually. As long as I don't wait too long, there should still be some nice hot water at, what, 100 degrees centigrade there, which is the required temperature for making tea. It can't be even 1 or 2 degrees less. You know, there are all these tea fanatics who tell you it's got to be absolutely boiling water. Looks like I've got some there, and the nice thing is it'll stay at 100 degrees centigrade for a long time there while it's boiling. So we'll get back to that in a few, well, a certain number of minutes. All right, so let's see if you understood this point about the enormous heat capacity of water. What I mean by that is it can absorb an enormous amount of heat energy and still not change its temperature by very much. So, for example, suppose you were in the kitchen. So this is actually a concept from chapter 19, but I thought it made sense to talk about it here. You want to get rid of the heat really fast. For example, suppose there's a kitchen fire. Now, I'm not going to do that demonstration in here, but obviously one reason you might want to spray water or mist on a fire is to simply take away the oxygen to stop the burning. But another reason that it's a very good idea to do it is because the water spray has a huge heat capacity. So it will take an enormous amount of energy from the flames and then just put it into the water by raising its temperature a little bit. So water is just great for holding heat and cooling other things off because water can accept heat. It's a great storage capacity. Now, as you recall from the table on the last slide, copper here has a very low heat capacity. So that will change temperature very easily. That actually would be good in the kitchen if you want something to change temperature really quickly. Metals just heat up as soon as you put any energy in them at all. And they give the heat away as fast as they can. So let's see, which one would be worse for you to touch? Water which has just been heated up to 100 degrees centigrade, like this here. I'm not going to do that either. You guys are sadists here. Or water which is an equivalent amount of water, vapor, which is steam coming out here. Well, this is a little bit paradoxical. It'd be hard to make as good thermal contact, but in principle, the steam has much more energy in it. We'll come back to that. Why does the steam have much more energy in it than the actual water, even though they're both the same temperature, 100 centigrade? Because when it turned into steam, those are little gas molecules. The bonds roughly holding the water together into some kind of connected fluid have been broken, and an enormous amount of energy. It turns out a huge amount of energy was required to break up the water structure, break it up from a liquid into a solid on a microscopic scale. And in fact, in the case of water, you might be amazed at this. I'm kind of amazed. If you have just 1 kilogram of water, it takes 2.3 million joules simply to convert it, even without changing the temperature, convert it from liquid water at 100 C to steam, vapor, water vapor at 100 C. That is an enormous amount of heat that just went into what? Breaking up the liquid. That must be what we would call the heat of vaporization. All right, getting back to the idea of heat capacity, things are just a little bit more complicated in real life than what I had told you earlier. Earlier, we discussed the kinetic theory of gases, and the idea is that the temperature of a gas, remember what the temperature was? It was simply a measure of what the kinetic energy of the individual particles was. So here, for example, might be an oxygen molecule bouncing around in this room. There's one oxygen there, there's a molecule O2. And so it's going around in 3 different directions. Each one of these directions has an average energy of a half kT. K is that Boltzmann constant, a fundamental constant of nature. T is the absolute temperature. And since there are 3 directions that this can fly around in, the average total energy of the kinetic energy is 3/2 kT. That's basically another way of looking at our ideal gas formula. That's the kinetic energy, and of course when this bounces off the wall of a container in 1 dimension, it will transfer some of its momentum. It will produce a pressure. But and of course that also would be true if I had monoatomic gas, for example helium. Helium doesn't make molecules, so you just have individual heliums bouncing around, producing pressure also obeying an ideal gas law. But there's one thing that we left out. When you have molecules, for example, here's an oxygen molecule which has 2 atoms in it, they can do other things besides just simply translational motion. Besides just moving around, there's a certain amount of kinetic energy associated with whichever direction it's going. It has X, Y, and Z components of kinetic energy, but it also can store internal energy. So you might not have realized. For example, every oxygen molecule, unless it's at absolute 0, has the possibility, you can't stop it, on a microscopic scale, unless it's absolute 0, it's also going to be spinning around. So there's also a certain amount of rotational energy when you get a diatomic molecule, not possible with a monatomic molecule like helium. Helium can't do this, but oxygen molecules, nitrogen molecules, O2, N2 are going to spin. I'm going to give you an interesting guess here. How much And of course, these collisions between these molecules are happening millions of times a second. So a collision could change the velocity of this molecule, or it could hit it the right way and start it spinning faster, or it could hit it the wrong way and slow it down. So just as collisions between molecules transfer kinetic energy from one molecule to another all the time, just like I showed you in class earlier, the collisions are also going to have the chance, it's just, remember, random statistics, they'll have the chance of transferring rotational energy, that's an internal energy, into these diatomic molecules. So here's something I'll let you guess. In a gas of temperature T, which has diatomic molecules like oxygen, how much energy on average do you think the oxygen has internally saved up in its rotational motion? If you could get down there and look at them with a super microscope, electron microscope, and see them in real time spinning around, how much energy do you think it is? It's related to how fast they're moving. Want to take a guess? Turns out it's an energy on average of about kT. That's right. kT is the amount of energy that any kind of motion of a microscopic particle is going to acquire if it's in equilibrium, thermal equilibrium, with all of the other molecules that are around it, which also have a temperature T. So it's not just the kinetic energy of the molecules moving around, bouncing around, it's also their rotational motion. If there were very, very high temperatures involved, there's even an additional kind of motion which a diatomic molecule can have. It can vibrate, oscillate, like on a spring. That requires very high temperatures to happen, and so it's not happening in this room very much. But at a very high temperature, like in a star or something, outer atmosphere of the sun, this would happen too, and that would be even another place where a kT amount of energy could be found internally in the gas. Anyway, so that's why diatomic molecules have a bit more energy when they reach a temperature T than monoatomic gas. All right, so here's going to be our formula for how much total energy is in a gas as of a temperature T. What I really want to know, I'm going to simplify it for the moment here. Let's just look at a monoatomic gas. Here is the definition of the heat capacity, C, for a gas. Remember, in the table I started the lecture with, we had the heat capacity for solids and liquids, and that was fairly complicated. Depends on the detail of solid and liquid. Wow, not much water left here. All right, just got to keep an eye on that. For ideal gases, it's going to be very simple. The amount of energy that you put into the gas, which goes into its internal energy, is going to be directly proportional to how much temperature goes up. You put energy in, you expect the temperature to rise, and what's the constant proportionality? You got it. It's the C, the heat capacity or the specific heat is what God, we're learning all these technical terms here. The heat capacity or specific heat of the ideal gas is how much temperature goes up when energy is put into it. Heat energy is put in. So there's another way of writing it. So what is this formula for a monoatomic gas? Well, remember, the only thing a monoatomic gas like helium can do is it can change. If you put more energy in, it can increase its y velocity, it increase its x velocity, and it increase its z velocity. There's 3 dimensions, and that's it. They each have half kT of energy, and so if you raise T, you're going to raise the kinetic energy in each of those 3 motions. So the ideal gas law gives you a very simple answer. The change of temperature for a change in energy, or the change in energy for a given temperature, is just 3/2 times the number of moles you have times the gas constant R. So that's going to be true. Now notice in this case I did not change the volume of the gas at all. I held that fixed. I just put energy in and let the let the atoms move faster. So this is basically another way of stating the ideal gas law for a monoatomic gas. We just have 3/2 number of moles times the gas constant. Now what if, wow, after looks like about 14 minutes here, I ran out of water here. It all boiled away. Wow, no tea. Bummer. All right. I wonder if we could have predicted that by understanding the heat of vaporization. Well, I haven't gotten there yet. I should have saved that dramatic tea for a few minutes later. I just didn't realize I had so many joules per second coming out of my burner there for 1 cup of water. It was a little more faster than I thought. Anyway, there's a formula for it. We'll see it in a minute. All right. So what we just worked out is the heat capacity for a monoatomic gas when I don't change the volume. So that is called C sub V, the heat capacity for a given volume. Now, let's suppose that we have, here's a very important diagram, the pressure volume diagram. Let's suppose that we start at a point C here. So we have, it looks like about 1 atmosphere, 100,000 pascals, and we have a volume of a gas, though it looks like it's a little bit less than 10 to the minus 3 cubic meters. All right, it's about a liter here. Now, there are 2 examples of what could happen when you put heat into the system. Here's our first law of thermodynamics. We could keep the volume constant, in which case we would be moving from C to A, right? The pressure would just go up. Or we could keep the pressure constant. How would you do that? You know the old drill. You have a container with a fixed weight like a brick on top of a piston. And so that keeps a constant pressure on the gas. As you add heat into it, what's going to happen? At a constant pressure, the volume would go up. So this is the path that the gas would take if you set up the brick situation with a constant pressure, or if you put it in a fixed volume with very rigid walls that cannot expand at all, unlike this piston arrangement here, then the pressure would go up as you put heat in. Well, those 2 different cases correspond to different heat capacities by a little bit. And I don't think I'm going to go through the derivation here. It's fairly simple. But anyway, I think I'll just give you the result. Here's the result right down here. If you were to keep the pressure constant, then the heat capacity, remember that's the change in energy corresponding to a given temperature change, that's going along this path here, is the heat capacity going at a constant volume, that's C sub V, plus the ideal gas constant R. So in any problem that I give you, we should be clear, and I'll try to make it clear, whether the volume is being held constant or the pressure is being held constant. And if the pressure is being held constant, then you can see that the heat capacity is larger by this extra factor of R. Now, what is the volume heat capacity for an ideal gas? I just told you earlier what it was for a monatomic gas. 3/2 times R. So let's see. 3/2 times R plus R. If the pressure were held constant, that would be 5/2 R. Now, there's an additional degree of freedom that I just mentioned when you have a diatomic gas, such as the gas in this room. And so then the volume heat capacity, C sub V for a fixed volume, is 5/2 R, because some of the energy goes into making the diatomic molecule spin faster, and some of it goes into making them move faster. So it takes more energy to raise their temperature, because you have to feed all of those different degrees of motion or degrees of freedom. Anyway, so there are the formulas for an ideal gas, and they're pretty simple. to remember. So simple that you might not even realize that that's the definition of heat capacity for an ideal gas. All right, so there's a summary of our formula for an ideal monatomic gas. You just add NR to what CV was. CV was 3/2 NR, so it comes out to 5/2 NR. All right, that's all I've got to say about that. Now, for the remainder of the lecture, getting back to my cup of tea here, I want to look at the situation when an ideal gas law no longer applies. And you can't treat the little gas molecules as little billiard balls that are rotating around and bouncing around. It breaks down. Well, where is it going to break down? It's going to break down, for example, as we start cooling the gas, lowering the temperature. So here's the ideal gas law on the left. And you'll notice that for a given temperature, there's a high temperature there, at a given fixed temperature, P and V are just inversely related to each other. In other words, the product of P and V is a constant. Yeah, sure, it's a constant. If I haven't put any gas in or taken it away, it's just N, the number of moles, RT. And T is a constant here. It's T4. If I were to drop the temperature down, then the product of PV is still a constant, but it's a smaller constant. So there's a PV curve for lower temperature gas, and still following an ideal gas law. I guess that's Boyle's law is one version when you fix the temperature. If I fix the temperature at a lower temperature, I still have P being proportional to 1 over V. Or if I flip this around, V being proportional to 1 over P. PV equals a constant. However, what if I keep dropping the temperature more? We might start deviating from this ideal gas law. So here's an example on the right where that happens. At some point, the pressure isn't changing as much as the volume changes. You notice that kink in the curve, and it gets more kinked, and finally you realize, my gosh, I don't have like a vapor anymore. It started to condense into a liquid. And then, of course, new forces. It's not just little isolated billiard balls that are spinning around. It's going to start feeling a crystalline lattice structure as the molecules are so close together they start sliding and feeling each other's collective effects. That's a liquid. So in a PV diagram, you'll notice these distortions happening. And so right there is in this diagram is a boundary point where for that combination of pressure, that combination of volume, that combination of temperature, the gas is just condensing down into a liquid phase, or vice versa. If I just were to raise the, let's see, if I were to raise the pressure a little, well, if I were to raise the temperature a little bit, it would start going from a liquid into a gas. And over here is a point where there's a boundary point also between liquid and gas phase. All right, let's look at a more general PV diagram. This is very useful if you're interested in the three different phases of a substance. There's, of course, the solid phase, there's the liquid phase, and then there's the gaseous phase. Now, generally, you probably were thinking, I thought that it's just a function of temperature. Some people might have had this impression if you haven't been through physics before. So you start at a low temperature. See, the x-axis here is temperature. You start at a low temperature and you're thinking it's going to be solid. It'll be in a fairly rigid, but vibrating, because it's not at absolute zero. It'll be in a fairly rigid crystalline structure of a solid. And if I raise the temperature enough, then the bonds get looser and eventually they get broken so that pieces can slide back and forth between each other. And that would be the phase of matter called a liquid. And if I keep raising the temperature after that, the internal kinetic energy will be so violent that it'll break the molecules and the atoms free completely, and they'll fly apart as a gas. They will vaporize. So that's what you were thinking. Heated up solid, liquid, gas. Ah, yes, that's right, but it depends on the pressure that the material is under. So, for example, at lower pressures, once you get below this magic thing called the triple point of a material, at lower pressures, there is no liquid phase possible. The solid material, when you warm it up, it simply sublimates. It goes from a solid directly into a vapor. That, for example, is what carbon dioxide does when you freeze it, so-called dry ice. Frozen CO2 warms up, it goes straight into carbon dioxide gas, vapor. Now, another thing that you notice in reality, if you can really change the pressure around a lot, is that this pink line that we thought we know and love, the point at which a gas condenses or a liquid vaporizes, is a function of pressure. It depends on the pressure. So if we just measure this at atmospheric pressure, then we'll get one result, that there's a particular boiling point of a liquid. However, what if you went to a lower pressure? For example, what if you went to the high mountains, like Denver or the Rockies or something? Then that same liquid will actually vaporize, or will boil, at a lower temperature than it did at atmospheric pressure. And if you're at very high pressure, this would be uncomfortable. This is not just a trip into the Rockies here. But if you're at extremely high pressure, then there's a critical point where there's no clear difference between the material in a liquid and a gas state. So this is a very high pressure, and so you don't see those in daily experience, and I don't think they're going to ask you that on MCAT, because you rarely get that happening, for example, in a laboratory or hospital, unless there's an explosion, which there shouldn't be. Let's look specifically at my favorite liquid, solid, and gas, which is water. So here is the PV diagram for water, and at 1 atmosphere, it's what you already knew. The temperature is going up on the x-axis, moving along here at low temperatures from absolute 0 all the way up until about 0 centigrade. It was a solid. Then I go through MP, the melting point. At higher temperatures, it's a liquid. It's liquid water. And then finally, as I hit 100 centigrade, which is how the temperature scale was defined, I hit the normal boiling point of water. And hotter than that, it's going to be steam, water vapor. But notice that at lower pressures, the water boils at a lower temperature. This is why people always mess up the cooking when you're trying to boil like rice or something like when you go skiing and you're up in some mountain resort, but you're probably trying to save money, so you get a little crummy place that has its own kitchen in it. Wonder why you might do that. And so you've got a certain amount of cooking instructions, which like to make oatmeal or some whatever you have before you go skiing. And of course that is designed to keep the oatmeal at a certain temperature for 3 minutes, and then it'll all taste okay. So you run it for 3 minutes and it's boiling. So that's what it's supposed to do. Bring to a boil, maintain that boil for 3 minutes, and then you eat it and everybody says, "Dad, that tastes like crud." Right, because I had it at maybe 90 degrees centigrade for 3 minutes. It wasn't, right, with the water is boiling, it's not going to get any hotter because I'm at a high elevation. So you need special cooking instructions when you go to high altitude. And generally, you need to boil it longer because it's boiling at a lower temperature. How many people have had that experience? Or maybe I'm just a bad cook and I'm just using physics as an excuse. Who knows? All right. So the main point I want you to know for today is that when you cross one of those boundaries, for example, you go from a solid to a liquid, which is called melting, or if you go from a liquid to a solid, which is called fusion, there's a large change in the internal energy of the molecules there. So, why? Because to go to a liquid, many molecular and atomic bonds are being broken, and that takes energy even though there's no temperature change. So going from an ice to a liquid is going to release, it's going to take a lot of energy even when the temperature doesn't change from 0. Let's say you're at atmospheric pressure at all. How much energy are we talking about here? Well, for water, wow, 300,000 joules just to melt a kilogram of water. That is really a lot. Darn. Whereas changing at 1 degree, suppose the water was already melted, suppose it was like at 1 degree centigrade, changing it to 2 degrees centigrade only took 4,000 joules for the kilogram. But just to melt it alone, breaking those bonds internally there, took 300,000. So that's a lot more. And then for mercury, it's a smaller number, but all right, who cares about mercury? Similar deal, and this is really amazing. Now we finally get to my tea kettle here. Happens when you want to completely break all of the bonds that are holding a fluid together and shoot out all of the individual atoms or molecules as a gas. That corresponds to an enormous amount of vaporization. The heat of vaporization, whoa, look at that. As I said, almost 2.3 million joules to vaporize a kilogram of water, even though it hasn't changed its temperature. It's still 100 degrees centigrade just before and just after. This huge amount of energy is what it takes simply to transform it from liquid into vapor. Wow. So what happens then if you have a burner here which is putting out a constant number of watts, a constant number of joules per second was going into my pan? All right, that was how my experiment was set up. What is the temperature of the water going to be as a function of time? I could have started there if I was dumb. I could have put a block of ice from the freezer in there. Right? Suppose you start with a certain block of ice and you start putting heat into it with time. Well, first of all, the ice is going to, since it has a certain heat capacity, the more heat that you put in, the more the temperature goes up. That was in an earlier table. So it takes a while, and eventually it hits 0 degrees. Oh, wow. So time is passing. This is the amount of energy being poured in. This is the number of kilojoules going in from my stove here. Over an hour, that's a lot of kilojoules. Well, for a while, the ice warmed up. Then it hit 0 degrees. Then what happened? More heat's going in. It took this much time. This is more time than it took to go from minus 20 centigrade. It took more time to simply break the bonds, what's it called? The heat of fusion. I had to put in the heat of fusion here. It's called latent heat. I had to put in that much heat of fusion just to turn it into a liquid. Finally, so let's see, it took for this amount of liquid. By the way, you notice this doesn't say how much heat is going in, and it doesn't say how much water I have, or how big a block of ice I start with. But anyway, for this given amount, it looks like it took about a minute or two to really warm up, and then it took, I don't know, about 4 or 5 minutes simply to melt it. Then now it's above 0 degrees and it's a liquid, so the liquid water, that's pretty much, it's warming up here as I keep putting heat into it. Let's see, it goes through about room temperature about there, and that's where my little experiment started. I had room temperature, 1 cup of water in there, and I kept the heat on, and as you saw, in fact, in a matter of about 1 or 2 minutes, it heated and heated up until it was boiling. Did you see that? It reached the boiling point pretty fast. This is just the heat capacity of water. And then what happened? It stopped raising its temperature. It just got stuck for quite a long time at 100 degrees centigrade. That's kind of useful if you're cooking. Cooking is all about controlling temperatures. And so it had a very controlled temperature for at 100 degrees centigrade, because what was happening? All of this energy here, remember, 2.3 million joules per kilogram of water was going into not raising the temperature, but turning it into steam, vaporizing it, the latent heat of vaporization. And finally, after, well, in this case, this is if you had more water or less of a less efficient burner. Finally, it was all steam, and then it starts going up. The temperature of the steam starts going up because now you have the heat capacity of an ideal gas. The reason I mention this one is it's an absolute classic problem in the Malkan family. My dad always used to put a kettle on to boil water and then go off and do something very important, some kind of business or something, and then forget about the fact that the water was boiling. So let's do an actual problem now. This is a problem of my dad's tea kettle. Actually, it's a problem of my dad's tea kettles, because he probably burned about a dozen of them up in the course of his lifetime. All right, we'll work on this problem in a second. I'm going to just put in some representative numbers for a fairly realistic situation, but you'll see it doesn't actually matter what the exact numbers are. We're just interested in the rates at which the water will heat up and then boil. And that is going to be independent of what kind of burner I have or what quantity of water. In this particular problem, just to get specific, we'll say that you put the kettle on, you start from cold water at 20 C, and you're just told in this problem it takes 2 minutes to boil that water. This is fairly realistic. My dad was not willing to just sit there by the burner watching it boil for 2 minutes. He said, well, I can do some work. I can be productive and efficient in this 2 minutes, and I'll just remember to come back while the water's boiling, because it takes a long time before it all boils away. There'll be some hot water left at 100 centigrade here from my cup of tea. I don't have to wait here for 2 minutes. All right. For concreteness, I'm going to assume this is a pretty high power kettle here that puts out 3,000 watts, 3,000 joules per second, and that it all goes into the water. Let's say there's none lost to the air, or whatever. Okay, a little bit of heat was actually lost in the kitchen, but forget that. Now, in 2 minutes, then, how much power are we talking about? Well, that ought to be fairly simple. In 2 minutes, the 3,000 watts times 120 seconds, yes folks, that's 2 minutes, you got 360,000 joules injected of heat entirely into the water. All right, and that was enough to get the water up to the boiling point. Notice in this problem it says begin boiling. So just where it's just starting to boil. So all that it really did is the 360,000 joules was enough to change the water temperature by how much? From 20 to 100? By 80 degrees. So delta T is 80 degrees. Here's the mass of the water. I think I want this in kilograms. And there's the key thing I need. What is the specific heat, or the heat capacity of water? Well, you remember that. How many joules does it take to raise 1 kilogram of water 1 degree centigrade? You remembered it right. 4,200 joules there for 1 kilogram. And now we need 80 times that, because we're raising it 80 degrees to get it up to the boiling point. 80 times 4,000, wow, it's about 335,000 times whatever the mass is in kilograms. Well, let's see. This is equal to, this is the energy that had to be absorbed. This is the energy available from the kettle. So you can see that M here must have been a little bit over 1 kilogram of water, 107 kilogram water. So that's the specific problem that we're given here of a 3,000 watt heater and 2 minutes to boil. If, of course, I had a less powerful heater, then I would have taken either more time for a kilogram to bring to a boil, or if it took 2 minutes, it would have been less water. The results, though, are going to come out the same anyway, because those things cancel out. Because if you just have more water, it takes longer to boil, to come to a boil, and it also takes longer to boil also. What I'm asking in this question is, what is the proportion or the ratio of time it takes to bring to a boil versus boil all the water away? What's the ratio of those two times? And that just depends on the latent heat of vaporization of water and the heat capacity of water, and those don't change. That's true for all water, any quantities, in any kitchen with any kind of heater. Now, we've figured out in this problem we have 1.07 kilograms of water. How long, once I brought it to the boiling point, is it going to take to actually boil that whole kilogram of water? Well, here's the big number, 2 million joules. 2256,000 joules times 107, got a little more than a kilogram. I need 2.4 million joules to boil all that water away, and yet I'm only supplying the water at a rate of 3,000 joules per second. So I got 2.4 million divided by 3,000 comes out to about 800 seconds. So if it took me 2 minutes to bring the water from cold up to boiling point, it's going to take me another 13 minutes before it all boils away. Seems pretty good. First, I can go get some work done for 2 minutes or whatever. All I have to do is come back, I don't know, 5 or 6 minutes later, and there still should be plenty of boiling water for me to make my cup of tea, right? This is, what is this? This is almost 7 times longer. Right, so I save the 2 minutes by doing some productive work, and as long as I can come back in the next 13 minutes, I'm not going to burn up the tea kettle. But for some reason, he just kept burning up the tea kettles. He knew this instinctively. I don't think we'd actually worked it out mathematically, that you've got to come back in a good bit less than 6 times the amount of time it takes the water to boil, or all you're going to have is a burnt up tea kettle waiting for you. So fortunately, tea kettles, weren't that expensive. So I would say, like every Father's Day, he got a new tea kettle to replace the last few of them that had burned up. But of course, if we had just done this computation, we would have, or I guess we'd used a timer. Later on, they invented tea kettles with timers and shutoff valves and fancy stuff like that. But anyway, you can look through all of the numbers in this problem and change them. For example, maybe I'll give you a problem where this is a 1,000 watt heater. Or I'll give you a problem where it takes 4 minutes to boil the water. Well, the answers are going to come out the same. It's still going to take 6.5 times more time after you brought the water to boil it all away, because you're just comparing the latent heat of vaporization with the heat capacity here, and that comes out to be the same ratio for any quantity of water if you want to raise it 80 degrees and then boil it. So the result does not actually depend on knowing how hot your heater is or how much water you have. I just gave those as some specific examples so you could work out something concrete.